Last time we saw that machine learning replaces handwritten rules with rules learned from data. But how does a model actually learn those rules? For a huge chunk of modern AI, the answer is a neural network. A neural network is just a stack of simple math units wired together in layers that gradually transforms raw input into a useful output. It sounds abstract, so let's build one piece by piece, starting with how data even gets in. Every neural network starts with an input layer. Raw things like an email, an image, or network traffic don't mean anything to a machine directly, so they first get converted into numbers. A word becomes a number, a pixel's brightness becomes a number, a packet size becomes a number. That list of numbers is what actually flows into the network, each number landing on its own input node ready to be passed forward. This numeric translation step is the same no matter what kind of data you started with. The basic building block of the whole network is the neuron. A neuron takes in several numbers, multiplies each one by its own connection strength, and adds the results together. Think of it as a tiny calculator that combines several signals into one. Every neuron in the network is doing this same simple job, just with different numbers flowing through it. The real intelligence isn't in any one neuron. It's in how millions of these simple sums combine across the whole network. Those connection strengths are called weights. A weight decides how much influence one input has on the neuron's decision. A large weight means that input matters a lot. A small or negative weight means it barely matters or even pushes the result the other way. When a network learns, it isn't learning new rules by hand. It's adjusting these weights, thousands or millions of them, until the combination produces useful answers. Weights are essentially the network's memory of what it has learned. Weights alone aren't quite enough. Each neuron also has a bias, a single extra number added to the weighted sum. The bias shifts how easily a neuron fires, the same way a strict versus a lenient judge might need more or less evidence before ruling. A high bias makes the neuron trigger more easily. A low bias holds it back. Bias gives every neuron a bit of built-in flexibility, so it doesn't just react to inputs, it reacts based on its own adjustable threshold. After the weighted sum and bias are combined, that raw number passes through one more step, the activation function. This function decides the neuron's actual output, often squashing the value into a useful range or blocking it entirely if it's too weak. Activation functions matter because they introduce non-linearity. Without them, stacking layers would be mathematically pointless, just one big straight line. With them, the network can bend and combine signals in ways complex enough to recognize things like a phishing email or a malicious file. A single neuron is limited, so networks group many neurons side by side into a layer. Each neuron in that layer sees the same inputs, but with its own separate weights and bias. So each one learns to notice something slightly different. One might respond strongly to certain patterns, another to completely different ones. Stacked together, a layer turns a handful of raw numbers into a richer set of learned signals, ready to be passed on to whatever comes next. Between the input and the final answer, networks often include one or more hidden layers, so-called because we don't directly see their output, only their effect on the final result. Each hidden layer takes the previous layer's output as its new input, combining simple signals into increasingly abstract ones. Early layers might notice edges or basic patterns. Later ones combine those into higher level concepts. Stack enough hidden layers and you get what's called deep learning, a topic we'll dig into fully next time. Eventually, the signal reaches the output layer, the network's final answer. Its shape depends on the task. One neuron might output a single yes or no score, like phishing or not phishing, while others output a probability for each possible category. The output layer takes everything the hidden layers extracted and condenses it into the specific answer the network was built to give. Everything before it exists purely to feed this final decision the best possible information. Now let's trace the whole path at once. Raw data enters as numbers at the input layer. Each neuron in the next layer computes its weighted sum, adds its bias, and applies its activation function. That output becomes the input to the next layer, and the process repeats, layer after layer, until it reaches the output. This single left to right journey is called a forward pass, and it's exactly how a trained network turns a new email or file into an instant prediction. So where do the right weights and biases come from? During training, the network makes a prediction, compares it to the correct answer, and measures how wrong it was. That error then flows backward through the network, nudging every weight and bias slightly in the direction that would have reduced the mistake. Repeat this over millions of examples, and the weights gradually settle into values that produce accurate predictions. This is the learning in machine learning, happening one small adjustment at a time. This same layered structure powers a lot of tools security teams rely on. Phishing filters use neural networks trained on millions of emails to catch subtle red flags a rule list would miss. Malware classifiers learn to recognize malicious code patterns even in files they've never seen before. Intrusion detection systems use them to flag network behavior that just looks wrong. Understanding weights, biases, and layers isn't just theory. It's what lets you reason about why these tools sometimes get it wrong too. So a neural network is layers of simple neurons, each combining weighted inputs, a bias, and an activation function, passing signals forward until they become a final decision. Weights capture importance, bias sets the threshold, and layers stack that logic into something powerful enough to catch phishing, malware, and more. Next time, we go deeper, literally, into deep learning and what happens when you stack many hidden layers together. Subscribe so you don't miss it.